This is the key question. What do you think will happen if we figure out the fundamental theory of physics
Right. So,
outside of the intellectual curiosity of
okay.
us
So
descendant of
here's my
apes?
best guess. Okay. So if you look at the history of science, I think a very interesting analogy is Copernicus. Okay. So what did Copernicus do? There'd been this Ptolemaic system for working out the motion of planets. It did pretty well. It used epicycles, et cetera, et cetera, et cetera. It had all this computational ways of working out where planets will be. When we work out where planets are today, we're basically using epicycles. But Copernicus had this different way of formulating things in which he said, and the Earth is going around the sun. And that had a consequence. The consequence was you can use this mathematical theory to conclude something which is absolutely not what we can tell from common sense. Right? So it's like trust the mathematics, trust the science. Okay. Now fast forward 400 years, and and now we're in this pandemic, and it's kind of like everybody thinks the science will figure out everything. It's like from the science we can just figure out what to do. We can figure out everything. That was before Copernicus. Nobody would have thought if the science says something that doesn't agree with our everyday experience, where we just have to, compute the science and then figure out what to do. People would say that's completely crazy.
And so your sense is once we figure out the framework of computation that can basically understand the fabric of reality, we'll be able to derive totally counterintuitive things.
No, the point I think is the following: that right now, I talk about computational irreducibility. People, I was very proud that I managed to get the term computational irreducibility into the congressional record last year.
That's right. By the way, that's a whole nother topic we could talk about.
Right. Different topic. Different topic. But in any case, but so computational irreducibility is one of these sort of concepts that I think is important in understanding lots of things in the world. But the question is, it's only important if you believe the world is fundamentally computational, right? But if you know the fundamental theory of physics and it's fundamentally computational, then you've rooted the whole thing. That is, the world is computational. And while you can discuss whether it's not the case that people would say, well, you have this whole computational irreducibility, all these features of computation. We don't care about those because after all, the world isn't computational, you might say. But if base thing, physics is computational, then that stuff is, that's kind of the grounding for that stuff. Just as, in a sense, Copernicus was the grounding for the idea that you could figure out something with math and science that was not what you would intuitively think from your senses. So now we've got to this point where, for example, we say, once we have the idea that computation is the foundational thing that explains our whole universe, then we have to say, well, what does it mean for other things? Like, it means there's computational irreducibility. That means science is limited in certain ways. That means this, that means that. But the fact that we have that grounding means that, and I think, for example, for Copernicus, for instance, the implications of his work on the sort of mathematics of astronomy were cool, but they involved a very small number of people. The implications of his work for sort of the philosophy of how you think about things were vast and involved, everybody more or less.
But do you think so? That's actually the way scientists and people see the world around us. So it has a huge impact in that sense. Do you think it might have an impact more directly to engineering derivations from physics, like propulsion systems, our ability to colonize the world? For example, okay, this is like sci-fi, but if you understand the computational nature, say, of the different forces of physics, there's a notion of being able to, warp gravity, things like this. Like
can we make warp drive?
Warp drive, yeah.
Right.
So, like, would we be able to? Will like Elon Musk start paying attention? Like, it's awfully costly to launch these rockets. Do you think we'll be able to, create warp drive and
right? I set myself some homework. I agreed to give a talk at some NASA workshop in a few weeks about faster than light travel. So I haven't figured it out yet. But no, but
you got 2 weeks.
Yeah, right.
But do you think that kind of understanding of fundamental theory of physics can lead to those engineering breakthroughs?
Okay, I think it's far away, but I'm not certain. I mean, and this is the thing that I set myself an exercise when gravitational waves were discovered, right? I set myself the exercise of what would black hole technology look like? In other words, right now, black holes are far away. They're, how on earth can we do things with them? But just imagine that we could get, pet black holes right in our backyard. What kind of technology could we build with them? I got a certain distance, not that far. But I think so there are ideas. I have one of the weirder ideas is things I'm calling space tunnels, which are higher dimensional pieces of space-time, where basically you can, in our three-dimensional space, there might be a five-dimensional, region, which actually will appear as a white hole at one end and a black hole at the other end. Who knows whether they exist? And then the questions, another one, okay, this is another crazy one, is the thing that I'm calling a vacuum cleaner, okay? So I mentioned that, there's all this activity in the universe which is maintaining the structure of space.
Yes.
And that leads to a certain energy density, effectively, in space. And so the question, in fact, dark energy is a story of essentially negative mass produced by the absence of energy you thought would be there, so to speak. And we don't know exactly how it works in either our model or the physical universe, but this notion of a vacuum cleaner is a thing where, you have all these things that are maintaining the structure of space. But what if you could clean out some of that stuff that's maintaining the structure of space and make a simpler vacuum somewhere?
Yeah.
What would that do?
A totally different kind of vacuum.
Right. And that would lead to negative energy density, which would need to, so gravity is usually a purely attractive force, but negative mass would lead to repulsive gravity. And lead to all kinds of weird things. Now, can it be done in our universe? My immediate thought is no. But the fact is that, okay, so
once you understand the fact, because you're saying like at this level of abstraction, can we reach to the lower levels and mess with it?
Yes.
Once you understand the levels, I think
I know, and I'm I have to say that this reminds me of people telling one years ago that you'll never transmit data over a copper wire at more than 1,000 baud or something, right? And this is, why did that not happen? Why do we have these much faster data transmission? Because we've understood many more of the details of what's actually going on.
Yeah.
And it's the same exact story here, and it's the same. I think that this, as I say, I think one of the features of one of the things about our time that will seem incredibly naive in the future is the belief that things like heat is just random motion of molecules, that it's just throw up your hands, it's just random, we can't say anything about it. That will seem naive.
Yeah, at the heat death of the universe, those particles would be laughing at us humans, thinking,
yes, right.
that life is not beautiful.
Civilization.
Humans used to think they're special with their little brains.
Well, right, but also, and they used to think that this would just be random and uninteresting. Yeah. But so this question about whether you can, mess with the underlying structure and how you find a way to mess with the underlying structure, that's I have to say, my immediate thing is, boy, that seems really hard. But then, and possibly computational irreducibility will bite you. But then there's always some path of computational reducibility. And that path of computational reducibility is the engineering invention that has to be made.
Those little pockets can have huge engineering impact.
Right. And I think that's right. And I mean, we live in, we make use of so many of those pockets. And the fact is, this is, yes, it's one of these things where I'm a person who likes to figure out ideas and so on, and the sort of tests of my level of imagination, so to speak. And so a couple of places where there's sort of serious humility in terms of my level of imagination. One is this thing about different reference frames for understanding the universe, where like, imagine the physics of the aliens. What will it be like? And I'm like, that's really hard. I don't know, And I mean,
once you have the framework in place, you can at least reason about the things you don't know, or maybe can't know, or like it's too hard for you to know. But then the mathematics that's exactly it. They allow you to reach beyond what you can reason about.
Right. But so I'm trying to not have, if you think back to Alan Turing, for example, and, when he invented Turing machines, and imagining what computers would end up doing, so to speak.
Yeah.
And
it's very difficult.
It's difficult. Right. And I mean,
he made a few reasonable predictions, but most of it he couldn't predict, possibly.
By 1950, he was making reasonable predictions about some things.
But not the 30s. Yeah.
Right. Not when he first, conceptualized, and he conceptualized universal computing for a very specific mathematical reason that wasn't as general. But yes, it's a good sort of exercise in humility to realize that it's kind of like it's really hard to figure these things out. The engineering of the universe. If we know how the universe works, how can we engineer it